Okay, great. So last night we not you guys will be morning, right? Okay. In the morning, say
Yes,
we
yes, morning
discuss.
here.
Yeah, yeah. You guys, we discussed this, light absorption, right? And the reason for us to understand the light absorption because no, the generation, right? The generation typically you think about in this equation. In this equation, typically you can consider any positions the current come from what? Diffusion, right? And then uh, and then the next mechanism for the current or charge to add into the device is what? Generation, right? And meanwhile, you have what? Recombination. That's why basically if you think about that diode, we talk about, I don't need to draw that maybe. I can draw that now. Okay, here. Think about the diode, right? This is what? This is the N, this is the P, and this is the depletion region here, right? This is the depletion. Okay. Any position inside you see here. This position, you see how much charge or how much current is there you have there, right? Depends on how much it diffused to here, right? Okay, that's by this guy, right? And then how much what? How much generation? How much light absorption, right? This position, how much accumulation, right? How much recommendations, right? Recommendations, and then you have what? You have full emission, right? That is a radiative. There's other kind of recommendations, right? So basically, three mechanisms: one, diffusion; second, generation by photon; third one, recombination. Okay, that's why you have these three parts. Now, diffusion is because we diffuse to here is positive, right? Generation is positive. Recombination is losses. That's why plus plus, and minus. Okay, so that's why we care about the generation. The generation basically, especially under elimination, you know that generation is from where? From the uh, light absorption. That's why we link that to the light absorption. Light absorption basically, if I know how much my light coming here, you know, then how much go out, I will know how much absorbed inside this region. Basically, you have incoming light intensity, subtract, you know, minus that outgoing light intensity, okay? And then the incoming one is equal to what? Equal to typically, if you allow your light transport this distance, and then whatever light here that gets into the materials, multiply what? E power minus x, alpha x, right? See, this equation tell you whenever you get deeper to your what? To your materials by the depth of x, that's how much light will be stayed there, okay? That's the light intensity at that position. Since here you have reflections, right? Reflections, that's why 1 minus r, 1 minus r, then multiply the initial photoflux or light intensity, and then multiply the distance is traveled, e power what? Minus alpha x, right? And then that's these positions, right? These positions, right? That's what's the light in this position. When it's go out, it's that position, this much. The difference will be how much absorbed by that materials with with thickness as delta x. Okay, that's how you get here. You get your derivation. This is derivation. Okay. So with that, now we got the derivation. We plug into the what? These equations, and then we also apply what? We also apply the boundary conditions. Right? Boundary conditions. This is something we talked about before. You remember what we discussed here when we talk about the diode. You know, I'll still remember when we talk about diode. Here, you see that, you know, is this, is exactly as the position, at these positions, as edge, right? If you see this depletion region, at this, it's here, okay, it's here, okay. You look at in this region, at this edge, XP, XP there, bar there, and then what you see, that's the boundary condition. There's a lot of boundary condition you can use as XN bar there, okay? These two positions tell you the boundary conditions. At this boundary condition, you see electron is this much, okay? Yeah, that's how you get the boundary condition. You remember the boundary conditions here? That's exactly the same as you see there, right? And then so delta x, delta n, what is the excess charge at Z minus XP? Would be what? Would be this guy minus what? Minus the initial one, right? We go back there again, right? See this part and this part minus this part. Okay, that's what is here. It's this. This tell you what XP at this position. That's the boundary conditions. Okay, that's the boundary conditions. That's one condition that we found. Typically all the differential equations you need the boundary conditions so that you can find a unique solution, right? Without that boundary conditions, you cannot find a unique solution. Okay, and then a lot of boundary conditions. As this is a secondary differential equation. You have what? You have delta n, and you have delta n. You have tau, right? You have x, right? So that's why you need two boundary conditions. Okay, this is secondary. Okay, the first three you just need boundary conditions. Secondary you need two boundary conditions. Okay, and then the second one is this. You see here the contact when x equal to contact. What happens there? The diffusion. The diffusion has the contact. See, this is a short diode or long diode. Depends on short diode or long diode. Okay, so you see here, uh, this should be the short diode, right? Why is that? Typically, the solar cells, you don't want a long diode. You want what? You want the charge, right? You want the charge get out of this diode, right? So this has to be short diode. Otherwise, if your thickness is longer than the diffusion length, a lot of charge cannot reach to the contact. Okay, so that's why you see here at the surface, if you know the contact surface recombination, that all the delta n will be recombined at that contact because they all reach their diffusion length is longer than the thickness. Okay, so all of that has been recombined there. This is second property boundary condition. Now you have two boundary conditions. You have this differential equation. You can figure out that. That's basically you can solve that into these kind of equations. Okay, this is solution. The GIAN. Okay, that GIAN. This is GIAN here. Okay, GIAN is equal to this part two terms. One is here is very complicated. Okay, one is here. The second term is here. The second term is here. Okay. That's basically when you apply these boundary conditions into this secondary differential equations. Okay, this actually is pretty. If you think about this, is ordinary differential equations, ODE, right? It's not very difficult, right? Then once you find delta n, from delta n, the G equal to what? N mu e. That's gonna be Gn, right? So here, this n basically delta n, the delta n, because the electric field, at given conditions, you can know, or you can just put this as a variable, right? E is elementary charge, mu is what? The mobility. So when you figure out the delta n here, delta n here, you see the delta n. When you figure out the delta n there, you'll be able to find the current. So this one, when you calculate this, actually what you calculate, look at this, GN, we talked about this a few days ago, right? Not a few days ago, just maybe last slide, right? Or the day before, or the lecture either before this one or the lecture before last one, okay? So whenever you see this N, that means what? Electron as minority carriers in the P side, okay? That's why, look at here, electron diffusion length, okay? Electron diffusion, okay? And then you come here, it's actually what? It's also electron diffusion length, or this electron diffusion length. That's on the P side. Okay. On the P side, the Dn is what? Electron as minority diffusion coefficient, right? But when you think about the thickness is actually P, right? Thickness P, okay? That's TP, okay? TP, P. That's about this section, this part, okay? This side, okay? And then on this side, on this side, the current is this much, okay? Now let's take a look at this. Why this one? The first term here is called photocurrent. The second term is dark current, okay? Why is that? You can think about easily, right? The dark current, that. Dark current basically is photodiode, the diode, right? The diode has what? J equal to GIAN exponential, right? Exponential QV minus QV over KT, right? E exponential that part minus one, right? So you know this is what? Dark current, right? This is dark current, okay? The other reason you know why it's dark current, because dark current is not related to the photon, right? How do I know it's related to the photon flux? Because my BS, you know the BS there. Okay, now I circle too many. I'm going to remove all circles, okay? Then just circle the one I want. That's it. You see here? I know this photo current because I BS there. Because this term, the first term now relate to the BS, the photon flux. Okay, if you change that BS, you can use that light intensity. That would be the same thing. But light intensity you have to divide by what? The energy of each photon. So you still need to get the photon flux anyway. So this is the first term is photon current. The second term is the dark current. Okay, this one we will calculate only GN here. Okay, only GN here. GN lambda, okay? And the other one you need to calculate what? JP lambda, right? JP lambda, okay? Now let's see how to calculate JP lambda. Basically, the same differential equation, the same ODE, right? Ordinary differential equation. And then the similar, you know, boundary conditions, the two of them, right? And then you can calculate here, you know, will be JP, right? JP, you get the same thing. The first one, photo current. The second one is dark current. Dark current because you have this portion there. The second reason is that because that term is not related to the flux. It's kind of you know constant. Only depends on the applied bias, right? That's a diode, you know, property. Diode, you know, signature. And then the first part you have BS here, the same as what we discussed before. But that's why it's related to the light. You know, you have higher light intensity, higher photon flux. They have what? Higher current. That's okay. Good. And then you probably think about, you know, now we talk about this JP, right? This G what? GN. Now, what about in these regions? In these regions, typically in these regions, as we discussed before, right? You have the diffusion here, and then you have what? Special charge regions. You have very strong electric fields there, right? And then you either have recombination when we talk about that, you know, two diode model last night, right? That kind of recombination there, right? And then you have another, you know, diffusion, p side, right? So most of the time you will find out, you know, since the special charge regions, the electron transport very fast, or the charge transport very fast, you can get very high current there. So they do not dominate the total, you know, current you will see through the diode. That's why the total current basically will be emitted by the JP or I'm sorry, this is not JP, okay, this should be GN. I made a mistake here, okay. This should be GN, okay. This is confusing. GN and then here is what? Here is a JP, okay. Because inside you have P, Y, right? On the P side you have M because we talk about solar cells, right? For solar cells, the minority carriers, the electron goes off, you know, kind of opposite directions. Oh, I'm sorry. So here, since we talk about diode, okay, talk about diode. So this actually electron goes from the right to the left, to the right to the left. So since you have a lot of electrons on the right side, N side, the limiting point will be on the P side. That's why we use electron on the P side, and then we use hole on the N side, okay, as the limiting points for the current flow, okay, in the diode, okay. So that's the reason. And then whenever we talk about the diode current, let's still talk about the what diode, okay. If the photon energy will be good, the photon will be good from here to there, okay. That's opposite, okay. So that's why, you know, if you pay attention here, I'm not sure if you pay attention here, there's selective, you know, there's selective. See here, this selective, this is positive, right? That's why this photocurrent will go opposite directions, okay. So with that, now let's talk about the current in special charge regions, okay? The current in the special charge region. So in special charge region, basically assume, you know, similar as we did before, the special charge region starts from what? From the xn and then until reach to the end of xp, right? That's SCR, that's also called depletion region. In that depletion region, you think about incoming light have what? Incoming light at this, surface, at this surface. Okay, at that surface, you have light intensity 1 minus R, right? Then multiply the incoming, BS, that's the photon flux, and then multiply the light already transport the distance as what? Tn. That's what you see there. Okay. Tn there. Okay. And then when it go out here, it's basically this light already travel additional distance xm plus xp, right? So that's why the Tn there will become what? Xm. It's probably too small. I hope you guys can see what I'm talking about. Okay. Here. Okay. Because it's travel additional what? Xm plus xp. That's why you add that into the Tn. Okay. With that, since that's selective, right? The light intensity get reduced, right? That's why this guy minus this guy, what you get would be how much light absorbed in that depletion region, right? Incoming one, subtract the outgoing one, the incoming light intensity or incoming photon flux minus the outgoing photon flux, what you get would be how much absorbed, okay? How much absorbed in that depletion region, where's xm plus xp. Okay, that's a generation for that region. Okay, and then probably you want to know, how fast, right? If that charge generates there, they come out very fast, right? And then that would be probably just add into what? Add into my photocurrent, right? Not photocurrent. Yeah, that's a photocurrent. So, but how fast they get out? Do we have any losses there? Okay, for that you can figure out, the velocity of the charge generated in the depletion regions. So with that, I can think about if I know my, flat charge regions ways. You remember we talked about this before. Talk about how to calculate the ways equal to what? Square root of this guy, right? O epsilon, right? VBI minus what? AA, right? Divided by out here. What is something there and then what? 1 minus NA plus 1 minus 1 divided by NA plus 1 divided by KT. Okay, let me go back. Okay, we talked about this a few days ago. Since so many equations here, I kind of forgot what is that. This is probably at the earliest stage, right? Back here. Uh, just go there to see where is it. That equation we used to figure out, what is the width right here. Yeah, here. Okay. Oh, that's Q. Okay, look at here. This equation I'm trying to talk about. So this equation, I'm trying. That's what I'm looking for. Okay, that divided by Q. Okay, that's Q. I forgot. Okay. So from there you can figure out, the width, right? The width of these depletion regions. When you know the width, right, you can simply see if I have, a charge generated in midway, right, half of the width, and then you'll be able to calculate velocity or the time for it to come out. Okay, so that's just here. Okay, that's just here. Okay, half W, right? If you think about typically the depletion region, it's about 200 if you do the calculation. 200 micrometers, you can assume that way, hundreds of micrometers. And then half will be 100 micrometer, right? Divided by what? The velocity. Velocity equal to mu d, right? Mu is mobility, right? And the mobility is about, 100,000 for silicon. Sorry, not 1,000, not 100. 1,000 centimeter per V per second, and then divide by what? Electric field. Electric field, that's typically about, that much. This is a 10 power what? 5 in the depletion regions. Okay. Then what you see, you will find out about 10 nanoseconds for the charge to get out. So, okay. And then think about this, right? The lifetime for the current lifetime inside what? Inside the silicon typically is 20 microseconds. So this almost, 100%. Any charge you generate in depleted region, they will come out easily. They can get to the contact easily. You will not see much nations there unless you have a very bad junction. You have too much defect, too much impurities there, and then you cause issues for. So with that, I think we talk about we have talked about the diode, right? Long diode, short diode, and then especially when we talk about photo generation, we care about short diode because we want all the charge, to get out of the junction, like, get out of the diode. Okay, so okay, now let's take a look at the conventional Pin junction. So the conventional Pin junction typically is Pn plus. If you look at the junction from the top, you have N plus P, P plus, okay? N plus P, P plus. Look here, one here, plus. This is N plus, okay? Those are the junctions you typically get, okay? With that, typically the thickness of this N plus, I mean, a few hundred nanometers, the P plus also a few hundred nanometers, and then the P layer can be what, not 10, few hundred micrometers, about 1,000 times thicker, okay, 1,000 times. And then on the top, you typically have anti-reflection coating, right? That one. Why is that? Because you look at silicon wafer, right? I'm not sure if you guys see the silicon wafer. I can show you a silicon wafer right now. Okay, just. Right? If you guys see a silicon wafer, you can see this, right? You see this? I put this in front of here. I can reflect my screen, right? You see, whenever you see it's like a mirror, right? If this silicon wafer like a mirror, what do you mean? That means it has very high reflections, right? That's what you see here. That's why you add what? You add this anti-reflective coating there, okay? That's about the silicon wafer. Okay, that's the reason. If you think about silicon, it's a reflection itself can be 30%. Okay, can be 30%. And then on top of that, N plus is N plus you call it emitter, right? On top of that, you have the metal. Okay, you have metal, and then that's how you fabricate the solar cell. Backside, you typically have another metal, either aluminum or something, right? For the electron collect the charge. So as the electron goes over the top, holes go to the bottom, right? Then that's what you see there. The back contact will collect all the holes positive charge. The top contact will collect the negative charge electrons. Okay. The typical efficiency for conventional silicon solar cells about 13 to 16%. Okay, that's probably you see a lot of solar cells in the market. That's about that efficiency. Then now, since you know what this eliminate current, okay, eliminate current, okay, and then you use these conventional silicon solar cells as example. And what is it? What is your photocurrent, right? So the photocurrent, as we discussed earlier, right, when we talk about the short diode, right? You say that think about this. You have electron generated in the P layer, right? That electron will go to the top, right? N plus, right? And then you have this electron generated. What you can hold generated in this N plus layer. This one is this, right? This on the P side, right? So you call this GIAN, right? GIAN, minority carriers in the transport in the P side, the diffusion. And then if you talk about the N plus side, right? N plus side, you have this hole, right? You have the hole, right? And the hole be try to pass through what? Pass through the whole P layer, right? The whole try to pass through the P layer, and then that one. Or you can simply see a lot of pass through the P layer because the P layer is very highly active, highly what? Highly P-type doped. so it can transport P easily. So what I'm going to do, I will move this guy, to here, so that what I really mean is that I mean the whole transport in what? Whole transport actually. I'm going to make this shorter, okay? Really means that this problem really means the whole transport P in the end there, okay? End there, okay? Better express what I'm going to see. Okay, I add of some loads here, not load. I add some like add these equations, add this. I think the slide I send you is was does not have this. You can add by yourself, okay? So that's what you see here. On the N side, you have what? The whole transport, right? So that's why you have GN, JP, and also you have what? They have the depletion region, right? This is a depletion region, right? Between here and here, that's a depletion region. In depletion region, we just calculate SCR, right? So that's you have three portions of this total, photo current, right? As one is from the what? Electron as minority transport in the P. Another one is whole as minority transport in the M, right? And then in the SCR space charge regions, right? The depletion regions you also have charge, okay? One, two, three, okay? That's it, right? Now, if you think about the dark current, you may care about that, in this silicon solar cell, since it's still a diode, right? The photodiode, right? So in the diode, what is my dark current, right? Dark current basically goes what? Goes to opposite direction, right? Initially, we think when we talk about photocurrent, see that electron goes from P to N, right? Now the dark current is opposite. The whole goes from P to M, and then the electron goes from N to P, and then Z2, when you add bias there, that VA add the bias there, and then that current get bigger. That's why G number, times exponential, QVA over NKT, okay? And also you have what? You have this uh, depleted region, they have the charge, right? So depleted region, the charge is opposite. Why? Because what? Because the N side, we have all positive ions, P side have negative ions, right? So that's the electric field from top to bottom, right? That pro electrons to top and then hold to the bottom, right? That's exactly opposite of what? Of this current, right? So this current is opposite there. That's why it's minus. You see, this basically tell you GIAN. This tell you what? The GIAN multiplies that what? That potential VA, QVA of NKT. That's why the photocurrent is like, I'm sorry, the dark current is like this, okay? That's about the dark current. So from here, you have good ideas, what is the photocurrent look like in the solar cells, and then what is the dark current look like in the solar cell, okay? So with that, I think I can develop the entire equations, right, for the total illuminated current. That's equal to, the minority electrons in the P side, minority holes in the N side, and then the space charge region. Okay, and then if you care about the quantum efficiencies, the quantum efficiency is basically the number of photons generated, per number of, I'm sorry, number of electrons or holes generated per number of photons you absorbed, right? So you see the photon absorbed, that's the current eternal quantum efficiency, because you have reflection, you have transmission. If you remove that reflection or transmission, but typically transmission is not big, so that's why in the solution you only minus reflection. And then if you don't consider any reflection, you just consider all the sunlight come to my surface, no matter even it's reflected, I still count it. And that's called external quantum efficiency. See here E means external, here I means internal. Okay. So the total current is uh, when you talk about here, total current for each diameter, right? For each wavelength. Now, since you have many wavelengths, you integrate for all these at different diameter, you get the total current for the solar cell, so all for the photodiode, okay? So that's about, the basic equations or understanding for current, okay? So let's talk about the quantum efficiency. I think some students asked question about this before. right? If you want to know, my solar cells, whether it's my, emitter like this, N plus had some problem, or my junction had some problem here, or my, P layer had some problem is here, one, two, three, or either my back contact has some problem. I want to know where's my problem from, right? And then you can, use the quantum efficiency, spectrum action, right? Spectrum, called that quantum efficiency spectrum, okay? Quantum efficiency action spectrum, or the same thing. Then, but why is that? If you think about, uh, okay, think about my light absorption, right? Okay, so before I talk about that, maybe at the beginning, whenever you see this quantum efficiency spectrum like this, this wavelength, this is the efficiency, that's basically the maximum is 100%, right? Lower will be 0%. Then you'll see, at these regions, what happens there? Which light absorb that region? That basically what? That basically UV light, right? Light energy photon. When the light wavelength gets smaller, it's go to there until there's no absorption for the longer wavelength. So basically, the shorter wavelength absorb first, and then longer wavelength absorb later. Okay. Why is that? Because if you look at this, absorption coefficient, right? This absorption coefficient, this for silicon, right? Not only silicon, germanium, anything. This is wavelength. You see as the wavelengths get higher, the absorption coefficient reduce, right? That's why the overall, plot, what you see here, kind of like this, right? See? As the wavelength increases and then the absorption coefficient reduces, that means, as the signals get, that's what does that mean? That means a lot of, large energy photons absorb at the top, right? And then, as you go to later, then all the longer wavelengths will be more absorbed here, okay, in the latter region. Extreme half, top half will be more like larger energy photons. Second half will be smaller energy photons. So that's why I put here, if you look at the UV light, blue light, green light, red light, infrared, right? UV light basically absorb on the top, right? Even you have anti-reflective coatings, right? That typically it's transparent, right? It's transparent or is what? It's also the large band gap materials, right? Because you don't want to block any visible light. And then you go to N plus, right? N plus, that's blue light, and then go to green will be what? Will be depletion regions. When you go to red, that's more like the P layer, okay? And then you go to, infrared, that goes to back contact, right? Back contact. So that's why we can see here, if you see here, your QE is not good, your contact has some problem, top contact, emitter has some problem, or anti-reflective layer has some problem. If you see, in these regions, in the blue green, you will see the space charge regions have some problem. If you see the main body here, somewhere, like what, maybe 700 or 800, 900 degree, 900 not degree nanometers, and then you see problem from your P ligands. And then if you see, near fed regions, you have some problems on QE, and then that's it from what? From the back contact. Okay. So that's why the different wavelengths can tell you the properties or recognition or quality of the material. So you have junction problems, you have junction, inverse recognitions. That's all from this to be able to give a rough, estimate. So with that, I think, yeah, this about this. Look at here, right? Here about emitter, right? Emitter, right? And then here about what? Space charge regions, right? Here about what? Here about the recognition as a rare contact, this. If something happens here, that basically tell your P layer had some problem. Okay. With that, I think we talk about this. This is a typical, M plus. Typically we call that Pin Junction solar. Okay? And Venn diagram will be plotted like this. You should be able to plot this because we have taught you how to plot Pin Junction. N plus P plus N, or P plus N plus this, all will be the same. We also taught you about how to plot this semiconductor metal junctions, right? Metal junctions. Basically, what you align this beam level, right? And then you keep the offset of that, junctions between EC, same offset at the junction, and then you'll be able to plot it. When we talk about heterojunction, we'll teach you how to plot again, so that's probably give you a better idea. Okay. So this conventional one, the efficiency basically 13 to 16%. Then there's other solar cells, IT solar cells. That's basically you do a lot of texture structure on the top contact, and also you deposit amorphic silicon here structure. The only difference, you have this P plus, the P plus on the top, right? Because this one is a crystalline silicon solar cell. Okay, this one is different from the P plus we talked about before. Okay, the structure here is N plus. Okay, the wafer, the substrate is N plus. Okay, is N plus, different from the conventional one. You have texture structure on top, and then you have this P plus amorphic silicon and the I amorphic silicon as well. This N plus. We use N plus silicon, but here they use amorphous. Okay, you do the same thing for the bottom, right? Same thing for the bottom. This one is different because it's a P-type substrate, and then what they generate will be hole. Okay, hole transport to the top, and the electron transport to the bottom. Okay, then the band structure will be something like this. Okay, band structure. Okay. So this one is because it's from the structure point of view, try to reduce the losses from reflection, and also try to improve the hole transport properties, improve the hole collections. That's why efficiency will be higher, 20. Okay. Another one is on some power back contact solar cells. Then this one, what we talked about before, either the HIT solar conventional solar cell, where you have top is one contact, bottom of the one contact cuts through the cross sections, right? Top contact on top, light come from the top. But you can also build the all the contact at the bottom. Look here, right? PN, 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 right? That's interesting, right? Then because the silicon has a very long division length, right? Hundreds of micrometers, tens of micrometers. So you may not lose your charge that much, even your contact at the bottom. So because the electron all goes into the center and then come back to the electron at the bottom. Okay. Then you have all your texture on the top, light come from the top. Okay, that's it. Okay. Efficiency here is similar, right? 20 to 23%. I mean, the only benefit for this structure probably was the collection integration is easier because also positive negative contact from the bottom. Then you can think about this. You can collect this directly to there. This directly, and then you can seriously collect this device by itself instead of using external wire to collect them. And the last one is what? It's probably still the highest efficiency. This data pretty old, 20 years. Right? Silicon solar cell almost reaches the limit. That's about 25%. So these solar cells, I think, you have the P plus, the back contact, and then, see what is it? Yeah, you have top contact. Here is, top contact, bottom contact. You have two contacts, okay? And then you do the, instead of, many times you see the pyramid is kind of, like this. Now is the inverted pyramid, okay? Try to change the structure for trapping, scattering side, light scattering on light trapping side. Efficiency about 24.7%. Okay. This is actually part of the kind of conventional silicon solar cells, but they did more optimization of engineering on the. Okay, with that, that's about this chapters. I think this is probably most basic, most important chapters in the whole class, right? The next thing I think I'm going to talk about will be the heterojunction of thin-film solar cells. Okay. Stop sharing here. Just again. Share this new chapters. So I'm not sure if you guys still remember, when we talk about the derivations, right? We thought that single crystalline silicon, C silicon, right? Crystalline silicon, polycrystalline silicon, these are fourth generation. Second generation will be thin-film solar cell. Thin-film solar cells, of course, silicon solar cell, especially amorphous solar cell, so nanocrystalline silicon solar cell. These are also on to what the second generation. But many times, I mean, more frequently when people talk about thin-film solar cells, they either mean amorphous silicon solar cells or the compound semiconductors. Just did not mean that was from crystalline silicon, large silicon crystals, polycrystalline. Okay, so with that, now let's talk about the heterojunction. Is this maybe 5, 6, 7? Okay, this is right. Okay. So before we talk about the heterojunction, and then the slide before the chapter before we talk about what is a homojunction, right? What is a homojunction? Homojunction basically when you have the band gap is the same on P, same band gap on N, you form homojunction. So heterojunction, that's basically what? When you have this P and M, they have different band gap, okay? The band structure will be different, okay? That's it. So here you can easily choose different materials to make heterojunction, right? Because silicon band gap is about 1.1, germanium is about 1.6, right? And then the other materials or the band gap through here, right? We just take silicon, right? And then, for example, we just randomly select, gallium nitride, this band gap, this much, that much, When they form the contact, that junction called heterojunction. Because they are either from different materials or either from the same materials, but they have different band gap. This is two scenario, okay, two possibilities. Okay. So here shows the junctions for solar cell applications. These are common junctions. Conventional junctions, you will see what PN, P plus N, N plus P junctions, right? Then you see a lot of these, right? You see PN junctions in certain solar cells, and then, for example, P plus N, in the conventional silicon solar cells, you have N plus P plus, right? So you have the junctions for N plus P. They have what? P plus N or P plus P, right? And then the second junctions is called PIN, right? We also talk about PIN, right? Like amorphous silicon solar cells or gallium or these are PIN junctions. And then you have high-low, that's basically PP plus, N plus. You see that in conventional silicon solar cell because you have P, right? N plus P, right? And then P plus, okay? Then the last one is about Schottky contact or ohmic contact. We also talk about that, right? In the last night for my time. Your time will be today morning, right? So when you have more metal deposit on the surface, you can either form depends the Fermi level of semiconductors and also work function of the metal. You can either get ohmic contact or Schottky contact. Okay. So here shows the Venn diagram for silicon solar cells. We talked about this before, right? This just try to remind you, right? On the left side, you have what? You have this N-type silicon, and then you have Fermi level close to electron band EC. It's a Fermi level, right? This EC, N-type, and the P side, the P-type, you have what? Just opposite, right? The Fermi level get close to here. Then you have what? EC there, EV here, okay? With that, what you can see here, if you form the junction, you have QVBI, it will be what? The VBI would be the difference between what? Between EFN and then EFP. Difference here. That is that separation is the VBI, built-in potential. Okay, that's the built-in potential inside your devices. Okay. And then you know that when you dope this, you can tune this EFN, right? If you dope lower concentrations, like 10 power 13, this EFI gets closer to what? Get closer to here. If you dope that higher to 10 power 17, it gets to or 18, it gets closer to here. Now, if you move this to this way or that way, then this one, VBI will be get smaller or bigger. You see that? You can tune that, go to high or go smaller, okay? So overall depends on this. See? And D. So that means it's good. The VBI can be modified, can be tuned if you do that at different concentration. And then we also talk about how to draw that. I'm not going to repeat this, right? You already know that how to draw that, right? About, don't it? You start with what? You start with Fermi level. This one should be aligned with this, right? And then everything move up, right? Everything. This much difference. when you plot it, right? This much difference is the same. This much difference. If I stay here. Beam never aligned, right? Aligned. And then that's what we see, click here, that's the new junction. See here? That's exactly the same here. The only difference is what? You align the film never here, aligned, okay? Then how much band bending you have? This band bending from here to there. This for working never, okay, it's you think about here would be from there. VBI. That's VBI. That's the separation between EFC and I'm sorry, EFN and EFP. That's here. That's this guy. That's here. Basically equal to this. Any question here so far? So I know you can ask a question at the end of this lecture, right? But by the way, today we will have a solid cell testing demo here for you. So with that, I think we also talk about the metal semiconductor, right? Metal semiconductor basically what? If you think about this, if you have film nevers here, metal, and then semiconductor is here, that EF is here. Okay, basically, if you want to plot this, I'm going to show you how to plot this, right? Even we talked about this before, let's repeat this because sometimes this can be confusing. Okay, I know my metal is here, right? This is my metal film never. Oh, it should be stay there. Okay, and then this guy needs to go there, right? This EF on the what? On the semiconductor side should be go there, should be that. Okay, should be that. Move to there, right? Move to there. That's my EF, right? EF. Okay. Now since this one move up to there, my distance, from 4 this one, right? That's 4, right? And then this 0.2, 0.2 plus this one. Okay. Okay, let's do this way. This is the total band gap of 1.1, right? 1.1 minus what? 0.1, that's 1, right? So from here to there 1, that means this one move up also 1, right? Because I not 1, okay? This 4.2, right? This is 4.2, this is EF, here is this is 4 plus 1.1, that's what, 5.1. This is 5, right? Here is 5. If I write something here, this is 5, okay? This EF is 5 EV, okay, 5 EV. The separation between this and that is 0.8, right? 5 minus 4.2 is 0.8. So that's this guy should be, this guy should move up 4.8, right? Okay, and then this guy is 0.1 below. That's also go 0.1 below. You see here, 0.1 below. Okay, this is my new, on the semiconductor side. My EC moved there, my VV moved there, my EF is there. Okay, my EF is there. Okay, now you see here, because initially these points, on the EC, the separation is what? Is 4.2 to what? To 4, and then that cannot change. This cannot change, right? And then that's why you plug here, and then the same thing here. Okay, since this one shift by what? But this is move 0.8, right? Shift 0.8, and I do the same thing here. The other way, this doesn't change either. That's what you see there. Your band structure like this. That's the same, right? This position doesn't change, this position doesn't change, this position doesn't change. Position still the same, right? This is what the same distance there. Then your plot is like this. Okay. You see how I plot it? You can plot the same thing, right? Okay, that's how you plot what? How you plot these band structures when you form the contact. How the band bending look like, or depends where's the metal or film ever located, where's your EC, EV, and also where's the film ever located. Okay, the same thing you can do what for this, right? This is also metal semiconductor, but this one is what? This one is your metal goes to deeper into the band gap, and then it's lower than what? It's lower, it's higher. You call that either lower or higher, that's fine because it's negative, right? If you think negative is lower, if you think just absolute will be higher, okay? Then you can plot the same thing here, right? What do you have to do there, you move this guy to here, right? This is EF, right? You move that to here, right? And then this one move to there, right? Far away from there, the junction doesn't change. And then this move there, the separation of this is the same. So this is there, you see here, you know. Then what do you see here, right? Since at the junction, right? This position doesn't change. At right, junction that should not change, right? The junction change. Junction should not change. See that, right? That's what you see. This is new whenever this is what the junction look like, you know. When you see this, if the electron try to go through to the metal, it experiences what? The barrier, right? That's why it's called Schottky contact, okay? Before that, when the electron tries to go from here to here, it's just, you know, roll over, you know, roll down to the here, right? So that's just a energetically favorable, right? There's no barriers there. So that's called, you know, ohmic contact. It's called Schottky contact, okay? With that, we kind of recap, you know, about the homojunction, PN junction, homojunction for, you know, silicon, PN, and also the metal semiconductor contact, okay? So this example we talk about, okay, also this one is about what? About homojunctions, here about heterojunctions. Why? Because you have amorphous silicon and then the crystalline silicon, right? Crystalline silicon has band gap about 1.12 EV, right, EG. Then amorphous silicon has about 1.7 EV, right? So now you see the element is the same, right? Amorphous silicon, but one is amorphous, one is crystalline. Amorphous silicon also is what? Is direct band gap semiconductors. That's why if you want to make amorphous silicon solid cells, basically it can be thinner, okay, thinner. So next thing about the, you know, the band gap, when you use what? You know that when you deposit heterojunctions, you deposit two different materials. What does that mean? That means the materials are different lattice structure. The different lattice structure means there's a lattice mismatch, right? For example, if this is my substrate, right? It's my substrate. You know my lattice arrangement is like this, right? Okay. Now, if you deposit a lot of material, their lattice is smaller. You see this can form here, this form here, this form here, this form here, then this form here, this form here, here, here. And then you see suddenly there's what? There's something here. Look at this. The whole, you know, the whole section of that, you know, group of atoms or that collection of atoms cannot form bonding with anyone, right? If you see that, you will see what? You will see you have, I don't know why. Okay. You will see that red regions, that's the, you know, the line one. You can call that as the line defect, right? Line defect. A line of atoms there cannot form any bonds. You have dangling bonds there. They can trap electrons. They can trap holes, right? That's why you form a lot of, you know, effect at the interface. That's part of that, okay? So that's why many times people will use what? They want to use buffer layer. They don't deposit this, you know, different materials directly to that substrate. They want to deposit something buffer layer, something between, okay? So that buffer layer can help to serve the mismatch of this lattice or lattice mismatch, okay? So here shows an example of this cadmium telluride solar cells. Cadmium telluride solar cells, you know, basically you have cadmium telluride as a P, you know, P type, and then you have cadmium sulfide at N. Then you see this band gap is EG 1.5, and then this band gap EG is 2.42 UV, okay. And then you form the junctions, you know, their band gap are different, right? So this is called heterojunction, junction solar cells. And then here's another example, you know, I think we talk about this. You have amorphous silicon and then crystalline silicons, right? Amorphous silicon and crystalline silicon solar cells. Then what you see will be what? Will be this is 1.12 EV. This one is what? This is a amorphous 1.7 EV. Now you see, you know, this crystalline silicon. This is okay. You see, this is okay. 1.12 EV, and then here, right, amorphous silicon. See, the band gap is bigger because it's 1.7 EV, right? Okay, and then you have ITO after that. Same thing here as amorphous silicon. Either this is top side is here, bottom side is there. Okay, so basically it's the same. You basically have larger band gap. That's different from the Pin Junction silicon solar cells because their band gap is the same. So this shows how you will plot this heterojunction band structures. I think we can talk about this slide my time, tomorrow morning you guys time, okay? And I have 6 minutes. We can answer any questions for this lecture last night. Then after that, you can go to online to see how the solar cell is tested. Okay, there will be demo there for you. Okay. So now let's go ahead to take some questions, and then we'll continue this lecture tonight. Okay. Are there any questions? Yeah.
Yes, participants, they can raise their hand. Amit, can you take the question from the chat box?
Sir, as of now, sir, we don't have any question in the chat box. Sir, yes, one participant wants to ask question. Mr. Said.
Hello,
Yes.
I'm audible, sir?
Yes, please go ahead.
Yes, sir. Yeah, thank you, sir. This is a very nice information shared. My question is regarding the heterojunction structure. So when in the SCR, there is a band discontinuity delta EC and delta EV. So it will impact the electric field also, am I right?
It will impact the electric field and also the barriers for the electron hole transport. We're going to talk about that tonight. My time tonight, your time tomorrow morning. See, I stopped that chapter. Right after that, we'll talk about how that, delta E, delta EC, delta EV will impact. Yes, you're right. And then the impact for the hole and the electron can be different. Depends how the offset between EC and EV, between the N and P. Okay, we'll talk about that. Yeah, good question.
Okay, sir. Okay, sir.
If any other participants have any question, they may please raise their hand or they can ask in the chat box or in the question and answer section. Okay, Sumit. Yes, Sumit. Please proceed.
Yes, sir. Sir, I have a question. In organic solar cells, the excitation generation by the incident photon is dissociated at the donor acceptor junction. So the dissociated electrons move to the cathode and holes to anode. So then my question is, how can electrons move to cathode even though there is a Coulombic repulsion? Then how?
So that's okay. Uh, I used to teach a class called organic solar cells. And then that's typically after this. See here we talk. I was teaching. I'm teaching the fundamental of PV. That's basically start with silicon or the basic concept. And then another course I used to teach, is called OPV. And then that's tell you all information about organic solar cell, how it work, how the different structures. And then I'm not sure if there's an opportunity in the future, maybe Dr. Kumar can organize another one if that's you guys interested. I can teach that one for you. But here I can show you how that works. Just a second, okay? If I add a new slide here, I can. You talk about organic, right? Organic solar cells, if you think about the structure, it's like this, right? So you have, I plotted different color here. I should use highlight, okay? Organic, right? Like this, okay? Right. Okay, and then in between of them, and then I do another one here. Okay, and then this is the top electrode. Oh, now let me add another layer here. This called ETL, electron transport layer. That can be what? Then here, add another color. Okay, HTL is whole transport layer. Okay, whole transport layer, and then I will use this. Let's assume the whole transport layer, right? I'm going to switch this. I'm going to switch to this HTL. Okay, and then this is the ETL. Let me just erase. ETL. This is ETL. Okay. ETL. Change the color here too. Okay. Here and then. Top there, I'm going to switch color. The reason for that because I want the whole goes to top. Okay. Okay, and then the and I'm going to add what? Add something like particles inside, right? Add particles or whatever here, and another here. Okay, now let's see, right? Okay, you see the whole transport goes through, goes through here, there, okay? And then the electron transport goes through here, okay? This for whole, this for electron, okay? This for electron, okay? Basically, in organic solar cells, when you have, I will use different color. When you have light absorption comes, right? Light absorption comes, right? You generate electron hole pair, okay? Electron hole pair. This electron hole pair will recombine, will dissociate as interface, as this interface. The interface between the dollar. So here I use this color as dollar, between the dollar here. This is a dollar, this is a dollar. Dollar here, acceptor as this interface. And then your electron basically what? Electron basically goes these directions. Sorry, this is wrong. Okay. Electron goes here, bigger one, and electron goes to here, and then your hole, see here, will be okay. Maybe okay. See, I should just use this one. Okay. This is color. Right? Electron goes here, and then hole. I should draw this electron. Then the hole, hole will just go. You see that you have electrons here, hole is there. They separate as this interface, between the green and the blue. Okay, between green and the blue, So that's typically in organic solar cells, you want to form a network, right? The network, there should be a continuous pathway, for continuous pathway like this, for electrons, and then like this for hole. Okay, see, all the green should be connected with each other, form a good network. All the blue should form, good network for itself, and then inside when the excitation is generated either in this, N-type or P-side in the dollar acceptor, they will reach to what? They will reach to the interface, get dissociated, and then electron find its own network to go. Hole finds its separate, network for the transport. That's why the hole collect on the top, electron collect on the bottom. This depends. You have, you know, multi-structure or conventional structure. Okay, does that answer your question?
Yes, sir.
Okay, good.
Yes, sir. Thank you, sir.
So we have another question in the chat box. Let me read on his behalf. Mr. Kashif Nazir is asking, is there a possibility of spin-specific transport due to photon excitation?
See again. What's the
Yes, sir.
question? Let
Yeah,
me
he
go to the
asked.
chat box.
Yes, you can.
I stop sharing. I need to stop sharing. Okay, here. Box. Is there a possibility of a spin-specific transport due to photon excitation? What is this question about? Is what means spin? Photo, photon excitation, right? Photon excitation basically, what does it mean? Right, you absorb the photon and then you excite electron from ground state to excited state, right? Then the electron will be transported through the conduction band, hole transport through valence band. You talk about spin specific. Means spin up, spin down. Is that your question? I don't understand this question here. Can you clarify your question, please?
Mr. Kashif, I have unmuted you. You can ask your question.
Yeah. He add that here. Okay, is that the student's person who add that up or down?
Yes, sir. It's student. It's the same student who has asked the question. Yes, sir.
Oh, okay, good, okay. So for solar cells, doesn't matter, okay? Because when you talk about spin, it basically means the what? Basically means the magnetic property, right? You have magnetic property coupled with spin, right? But here we basically talk about electronic, electrical. So that spin, we never care about spin up, spin down. They have the same, okay? They have the same. Okay, the short answer, it doesn't matter, spin up and down the same, okay? Okay, good.
Thank you, sir. Yeah, sir. I hope he has got his answer. Yes, sir. He's satisfied with the answer. With this, I guess we have no more questions. Participants, if you have any more question, you can ask, or else we can move to tutorial session.
Yeah. Okay, great. You guys all have the link, right? Okay, new link, right? Okay, great. Okay, so I'm going to mute.
Yes, sir. Poojan, I have shared the privileges of presenter to you. Can you please confirm if you are able to share your screen?
Okay.
Yeah, we can
So
see.
I don't think we need to share the screen today. All will be demo. So we can share the thing. So can you see that?
Okay. Yes, absolutely, we can see.
So I think participants are the same as yesterday. I hope.
Yes. Most.
So can you hear me?
We can
Pujan,
hear
your
you.
voice is
Now it's good, I guess. Okay, sorry. Uh, we are just adjusting our headsets. Can you guys hear us now?
So actually yesterday we have fabricated this one solar cells, and today they are going to this one discuss how to characterize once you have fabricated these devices and how they look like. Yes, Pujan?
Yep, yeah, this is Raja. So
Raja, okay.
yeah, hello. Good morning, everyone. So yesterday we left off when we deposited rhodomain on top of PCBM and everything. And one step remaining for yesterday is the evaporation of silver, like C60 evaporation. Today we are going to show, like we will do both the process simultaneously. Like we will show you the characterization using IV as well as deposition of silver. So let me just start working on it. Okay. So as you can see, this is a evaporator setup we shown you yesterday. Let me know if you can't hear me. I don't know, like if I'm
No, you are fine.
if
You
my
are fine.
if my voice is fumbling or something. Okay. So already samples are in the mask. So we fabricated 12 samples last night, and we are out after the meeting. So this sample is with. This is not with PCBM. This is with C60 and BCP deposited on top of that. So if we can see the inner circle, that is C60 and BCP, the outer area which is left over is the perovskite cell. So we are just carefully gonna put it here. So now you can see the samples, right? Like this is the etched area for the bottom electrode, and the 4 electrodes will be etched on top of that. So this is the masking area. We'll just put it here carefully without disturbing the samples. And we are gonna clip them. Okay. So the samples are resting over there on the plate. Like that's gonna rotate. Rotary plate that's gonna rotate. And this is the silver plate where silver deposition pellet, where we're gonna put our silver pellet there. So these are the AG pellets with 99.99% purity and 1.8 inch by 1.8 inch diameter. One pellet should be enough to deposit 100 nanometer of film. So we're gonna deposit like 85 to 90 nanometer of film here. So you see, this is the silver pellet we're gonna use. Okay. So as you can see, I covered remaining 2 boards. Like this is the board for C60 and this is the board for depositing BCP. So depending upon the material, you're gonna choose your power. Normally silver is gonna deposit from the power 20 to 23%. After experiments, you will know like which power is good enough for depositing silver. And all the silver, like 85 nanometer of silver, we are gonna deposit in 25 minutes. So first step is to evacuate the antechamber to create the main free path like for your samples. Like what are the main free path required for your sample? It will start at 10 to the power of minus 6. So we'll go to the 10 to the power of minus 6 star, 9 to 10 to the power of minus 6 star, and start depositing silver. Before that, you may want to check. Pujan, can you turn on the rotary holder? Yeah. Yeah, and show it here. So you need to check whether it is touching somewhere. The rotary holder is touching somewhere, or is there any problem with the rotary holder? So it is fine. So we'll turn off the rotary holder now. And you can see the shutters here. This is shutter 1 and this is shutter 2. Close the shutter 2. So you see there is a shutter on top of silver. So there is no unusual deposition of silver. Like in the middle of the process, if you don't want to deposit any silver or something, you can close the shutter on top of silver so it won't evaporate. And this is the piezoelectric sensor we place. If I can show you the volt sensors, this is the piezoelectric sensor we will place in the system, which is with 6 megahertz frequency. And the health, like depending upon the health of the sensor, you're going to change the sensor. Like if the health is below 90%, can you show the health? Yeah. So if you see the life is now 98.13%. When it goes below 90%, like after maybe 5-6 depositions, it will go below 90%. Then you want to change your sensor. So now we'll close this is called as evaporator inner door. We're gonna seal it and press the inner door, evaporator inner door. Okay. So now the inner door is locked. You can't move it now. Once this is done, this is the chiller, which will cool our vacuum pump. So there is a turbo pump inside this one. The turbo pump needs cooling. So we're gonna turn on the chiller. So right now it is at 15 to 16 degrees centigrade. The water will be flowing here to the turbo pump, and it will be circulating around the turbo pump to cool it. And evacuation start. It will be little noisy, but this TP1 is the turbo pump, so it's gonna rise. Once this pressure, you can see the pressure is dropping now. Initially it was at atmosphere, now it is a 640 millibar, and our turbo pump is increasing. So slowly our turbo pump will go to 100%, and this evaporator pressure is gonna be 10 to the power of -6 millibar. So for now, we let it go to the evaporation. It will take 20 to 30 minutes to go to the 10 to the power of -6. Now we will start our IV. I just need some samples for IV. That's why I'm evacuating this one. Come to the IV system. So this is a typical, like if you can show whole system. So this is the typical IV system we are gonna use for measuring the IV characteristics of our perovskite films. You can measure anything. You can measure silicon. You can measure perovskite. If you know the area of your sample, that should be good enough. You can measure the sample. So there is the xenon arc lamp housing. There will be a xenon arc lamp. I already turned it on. Normally, you want to turn it on at least before 15 to 20 minutes of your experimentation, because that need to be heated up. The lamp need to be heated up to give you once an illumination. And the one you are seeing here, this is the source for the lamp. We are gonna turn off and turn on the lamp from here. And right now it is at 100 watts. Normally we do all IV characterizations at 100 watts to get that one sun illumination for each of the characterization. The sample you are seeing here, this is called the reference sample, and this is from NREL, National Renewable Energy Laboratory. So they will calibrate solar cells for us and send it to us. So typically this solar cell give you 1.64 milliamperes of current. So in order to set up the distance between your sample and the solar simulator, you need to know at which place you are getting 1.64 milliampere per centimeter square of current. So to know that, first you need to measure the IV for this sample, and you will set up 1.64 milliamps. There you will know like this is giving one sun illumination. Then what we are going to do, like we will just remove this and we will place our sample at the exact place to get that one sun illumination to our sample and measure the IV characteristics. So this typical instrument, this is the source meter. So this is Ketley 2400 source meter. This typical source meter will measure the current and power, like voltage, which is coming from the sample. So if you turn it on, You can see the screen. This is model 2400 Ketley. This comes with a software called PVIV 1.1. That is a software we will use to measure the forward and reverse bias characteristics of the sample. You can see this current microampere. Like when we connect the sample, this is gonna change depending upon the voltage we get. Typically for a solar cell, we expect the ideal VOC to be the band gap of the solar cell. Suppose if your band gap is 1.51 electron volts, theoretically your VOC should be plus or minus 0.2 of that one, that is 1.31 volts. But you know, the recombination and the shunt resistance and the layer to layer recombination causes a lot of VOC loss in our sample. So for a typical sample of MAPBI3, we will get 0.9 to 1.1 volts of voltage. So this is the computer setup for the sample. It takes little time. What happened to this? Okay, good.
So students may ask the questions.
Yeah,
If
you
they
can
have
ask
any
like you
in
can stop me
between.
anytime and ask the questions, not a problem.
So we have one question in the chat box from Mohammed
Okay.
Umar. He is asking, how does life in percent relate to life in time?
You are asking about
You have
the
shown in the thermal.
No,
you are
life.
showing your life
How
like
does
it's in the evaporator, right?
how does life in percent relate to life in time?
Or life in percent related to life in time. So time and percentage are not related. Typically, you will see life like before every fabrication. You will see the life in percentage. If the life in percentage is less than 90%, then only you are going to change the sensor. You
Yeah,
don't know
so
like for 6 fabrications it's gonna be less than 90% or 10 fabrications it's gonna be 90%. Typically for 6 to 7 fabrications, one sensor should be enough.
yeah, so basically what is happening in this one is a quartz crystal is there, and basically this quartz crystal is vibrating, and when material is depositing on this one, the resonance frequency is changing. So once the deposition is very high, in that case, what will happen, this one we cannot use for the again for multiple use this one, because this resonance frequency is already this one too much shift is there. So up to one limit, basically, we can deposit. Depend on the material also, how much we are depositing. We are depositing, for example, few nanometers, then we can use for the longer time. But if we are depositing in the
Can you
micron
decrease the volume?
then we cannot use for the multiple times. So this one is totally depending on the resonance frequency, how much shift is there, and shift is depending on the material, how much material is deposited on the crystal. Okay, any other question from the participants? Yeah, Raja, you can continue.
Okay. So first you need to set a recipe here, like this is the Oriel instrument test station version 2.1.1. So this comes with your PVIV instrument. So here is the typical recipe for our standard cell. My standard cell sample area is, this is already given by NREL. Okay. So when we are purchasing the sample cell, we know the area. It's 0.06 centimeter square, and irradiance is 1 sun. It depends, like which irradiance you want. Maybe you want to illuminate only 0.1 suns. That's fine. You can just set the irradiance here. And the pre-sweep delay, like for each sweep, how much delay you want, like 0.5 seconds, 1 second, 2 seconds, 3 seconds. And this is the bias direction, forward to reverse or reverse to forward. Like normally we do solar cells in forward, reverse, and reverse forward direction. So that's one. And this is the maximum reverse bias voltage, how much you want to put. Typically, we use this one for dark current characterization. When we are doing forward bias, we'll start from 0. And the maximum forward bias voltage will be the typical VOC of your cell. Like suppose if your band gap is around 1.51, you know you're not gonna get 1.5, so you'll get 1.2 or 1.3 for the maximum forward bias. And this is the number of sweep points. So depending upon the number of sweep points, like suppose from 0 to 1, you say like there is 100 millivolts, sorry, 1000 millivolts. In 1000 millivolts, it will take 100 samplings. Dwell time, we don't care much about it, and current limit is 30 milliamps, so that's fine. Like you can put 40, 50 milliamps, it's gonna calculate what current you are getting. This is for typical illumination. And if you want to measure the dark current, you are gonna put dark current shutter closed and R shunt voltage low and voltage high. So it will be typically from minus 0.1 to plus 0.5. So you'll see a dark current curve like a V-shaped curve when it is going from minus to positive. And after that, you are going to see the shunt resistance, after that series resistance. So when you want to see why you are losing VOC, why you are losing all the characteristics, typically you do dark current characterization. And from the illumination characterization, you're gonna get your JSC. So JSC is nothing but like normally we'll calculate ISC, which is depending on the area of the sample. And JSC is the one which won't depend on the area. JSC is the current density, which is milliamps per centimeter square. For each centimeter square, what's the current you are getting? That is called as JSC. And the typical voltage you are getting from the solar cell. And fill factor is like if you see it, let me load one thing. Cancel changes. Open. Okay, let's see. So here is the IV graph for this one. This is the VOC versus once you see the results, the ISC for this sample is 2.3 milliamperes. So this is showing in amperes here. When you calculate it is 2.3 milliamperes. So my device area is 0.09 centimeter square. That's why I'm getting 28.7 milliamp per centimeter square. And the VOC here is 0.359, like 0.36 volts. And the fill factor is 48.226. The fill factor shows how rectangular your IV graph is. Normally, you'll expect a IV graph, like in ideal case, the IV graph should be a rectangular one like this. But when it is falling like this rectangular area, it will show how much area you're covering with the fill factor. The more fill factor you have, the more you are going towards the ideal voltage characteristics. The lesser fill factor attributes to lesser efficiency. And it will directly give you the efficiency to like 4.98% of efficiency. This is for the solar cell, which we calculated earlier. Now we are gonna do for the typical solar cell, okay? Typical standard solar cell, how we are gonna set up the distance between source and our solar cell. Just put a report ID like maybe solar cell and operator, it's my name. And recipe you're gonna select as standard cell. Okay. So now this recipe is set up here. We'll collect the solar cell. So it's just like, it's not the standard one, but it works. So the positive is connected to the positive lead, which is connected to the PVIV instrument. In negative here, you can see we already marked it, the positive and negative. And this is your sample. The black one over here, this one is your sample. So we'll just put it in the sunlight path, light path. We can adjust the height of it. I'm just trying to see in the triangle here and the distance between the light and this path. So once this is set up, you're just gonna press the measurement. So this is connected to the positive and negative lead. This one is going to my PVIV instrument, and PVIV instrument is connected to a RS-232 supply, like RS-232 communication. That communication is gonna give command to this system when we need to measure the sample. So once you press measure here, you'll hear a beep sound, which is sweeping the voltage from 0 to like 0.8 to 0 volts. So once that sweep is finished, you'll see the VOC here, 0.42 volts, and JSC is 1.52 milliamps. The typical JSC we expect from this sample, sorry, ISC we expect from this sample is 1.64 milliamps. This is little lesser, so we are going to adjust the distance. So the distance can be adjusted in both ways. Either you can just move your solar simulator, or you can move your sample, or you can adjust your horizontal and vertical positions here. This is the horizontal alignment and this is the vertical alignment, and there have more things to adjust. Here is the adjustment for rear reflector. So there is a let me show you. Where is the pen? Okay, paper please. Okay, so that. So normally this is the xenon arc lamp. This is the xenon arc lamp which is present there, and there is a rear reflector in the back of that one. So it will reflect the light to the outer wall. So we can adjust the rear reflector using the back knobs, and we can adjust the height of this xenon arc lamp using the side horizontal and vertical positions. So horizontal and vertical positions, you are adjusting the xenon arc lamp itself, and the back ones, rear adjustment, you are adjusting the reflector adjustment. So if we can show there, when I am adjusting the horizontal position, it will move my illumination to left and right. I don't know if you guys can see that, and this will adjust the solar cell in vertical position. So either focus on this one, or you can adjust the distance, or you can adjust the sample itself. We can move the sample forward. I want to keep my sample position constant. That's why I'm moving this one. So now we'll measure again. So it will show you this current. See, this is 1.593. The ISC increased a little bit, but it's not still till my limit. I need 1.64 milliamps of current. I'll just adjust a little and measure it again. Normally for the newer version of solar cells, everything is stable. Like you'll get the setup and you don't need to adjust anything after that. But this is little older, that's why we need to adjust a lot of things. So this is 1.71, little higher. So this is 1.6 milliamps. So it's just like 0.02 milliamps of diversion over there. That's good enough for me. That's 1.66 milliampere. So that's good enough for measuring our actual cell. So this is the typical distance and xenon arc measurements here. And there is a cooling fan on this side. So this side there will be cooling fan for this total xenon arc lamp because the temperatures are much higher. So you want to turn off your lamp when the lamp is cooled down. So typically when you are turning it off, you'll turn off the lamp here and let the fan turn off. Then only you will turn off the lamp. Otherwise, it will form a black film on top of the lamp, and it won't give you the Bunsen illumination you wanted. So this is the standard cell. Now we will measure our solar cell. Like we'll take out the samples from the glove box and measure our solar cells. Those are little older, it will give lesser efficiencies, but you can see what's going. So meanwhile, in the evaporator, this pressure is dropped to 1.10, 1 into 10 to the power of minus 5 millibar. So till we measure our solar cell, it will go to 10 to the power of minus 6, and we will deposit our silver. Any question?
Yes, Nipun, you can unmute this one, students, if they have any question.
Participants, if you guys have any question, you can raise your hand. I'll unmute you. Don't have, I guess, sir. Till now, we don't have any.
Just checking if I close the door properly. If I don't close the door properly, then it won't evacuate. Just being extra cautious.
Sir, can you show this one after depositing these electrodes?
Yeah,
Yes, yes.
I'm gonna deposit in front of you. So we can just refill and show you the thing. So you see these fingers over here? So these fingers are touching that, and I'm gonna connect my electrodes here to collect the current. So I'll remove my solar cell. This is the standard one. And I'll place my sample exactly at the markings. Like you can put a permanent position, but our lab is relatively new when compared to South Dakota. As Dr. Mukesh know, in South Dakota, we used to have a optical table setup. Normally, we will do it on an optical table to get rid of any vibrations. Now our lab is in the middle of setting up, so we don't have an optical table right now. That's why we are doing on the bench. This is the okay. And this positive goes to the first one. Yesterday somebody asked me why we etch this one. So this is the positive electrode for me now. So on top of the transparent electrode, like transparent glass, like ITO, we deposited a AG finger. That is my positive. And the remaining 4 will be my negative ones. So I'm connecting in the third position. So I'm collecting current from my third finger. So I'll see if the height is matching. Yeah. So you can see we marked a circle over there. So we'll just match the height of the solar cell and the distance between the lamp and solar cell as well. Okay. So typically this one is called as light soaking because some solar cells work better with light soaking and some solar cells work better with lower temperatures. So we'll continuously blow air on top of that one. And if you can see this one, this is the 0.04 centimeter square mask we designed to measure the lower area. that is typically 0.09 centimeter square, and this one is 0.04 centimeter square. So again, I'll set up the recipe for this one. We already have the recipe for tin solar cell. This is the lead-free solar cell. As you know, these are typically having lower efficiencies. That's why I put the sample area is 0.09 centimeter square. Irradiance is 1 sun. Free field delay is 0.50 microseconds, seconds. And you see the forward bias, since I'm using the low band gap solar cell, I put as 0.8 volts because I know my voltage don't go beyond 0.8 volts. That's why it's just 0.8 volts. And number of feed points are 200. That means I want to consolidate more number of points in my 800 millivolts area. And the current limit is 30 milliamps. Hope I'll get more, I don't know. So just click on measure. Then you'll hear a beep sound. You can see the current here. 8 milliamps, 6 milliamps, 1 milliamp. Again, 1.8 milliamps, 1.9 milliamps. Okay. So my VOC is 0.38 volts and current is 1.9 milliamps. That is 21.9 milliamps per centimeter square. So this is the ISC. This is the and this is the JSC. That is the current density. 21.9 milliamps per centimeter square. And fill factor is 62.06. And my efficiency is 5.2148. So this is the typical IV graph for my solar cell. And this like this app features some more things. This is the VOC versus ISC fitting graph. So when you see here, you can see the series and shunt resistances. See, this is R8 VOC and R8 JSC. So you want this one to be much higher than as possible, like the shunt resistance should be in kilo ohms and the series resistance should be very low for your solar cell to be efficient. And this is the total power graph. So how much power you are getting from the solar cell. So all these things you can get from one single fabrication. You are going to get all these things. So we can set up the cell temperature too, R shunt, cell temperature, and exposure time. So this is the typical time I'm exposing my sample to the cell. Like when I'm measuring something, I'm exposing 13.94 seconds to the sunlight from 0 to 0.8 volts. So for reverse bias, we have one more recipe. So if you remember, this is 0 and 0.8 volts. And for reverse bias, we'll just reverse this one, 0.8 to 0 volts. And the bias direction is from reverse to forward. If you go to edit, forward to reverse and reverse to forward. Save, turn, and measure. So it's going to take 13 seconds exposure time. See, 13.69 seconds of exposure time. And my VOC is 0.386 and JC is 0.00190, that is 1.9 milliamp. And GAC is 21.12 milliampere. And my efficiency is 5.01. So there is a term called hysteresis. The difference between the forward and reverse is called your hysteresis. The hysteresis is 0.21%. So 5.01 and 5.21. There is a 0.20 hysteresis in between my forward and reverse. So that is how we're gonna measure the solar cell. We are up for any questions. If you have at this point, then we are gonna deposit silver. Or if you want to do one more solar cell, we can do that now.
Hello, Raja Amit this side.
Okay.
I have few basic questions.
Okay.
First, I would like to ask that this 3M connector you have connected to the solar cell.
Okay.
Yeah, is this connector is customized or it is readily available in market?
It's little customized, but most probably it's readily available because when you search for a IC, 8-pin IC tester, then you'll find this 3M pin directly in the market. You can take the 14-pin, 8-pin, or 6-pin.
Okay. And another question is like your this PV-IV setup.
Okay.
The same source meter we have here in our lab, but
Okay.
we have the system software provided by Ketle itself, Kickstart.
Okay.
So this software is you have purchased from some other company or from the same Ketle itself?
This instrument we purchased from Newport actually. This whole instrument because we purchased EQE, that external quantum efficiency instrument, and this Ketley instrument from the same Newport. So the Newport provided the software for us.
Okay, AKV is what?
Which one?
You asked the source meter and another instrument AQV.
EQE, like external quantum efficiency.
So it is which instrument?
That will measure the quantum efficiency. That will measure your incident photon, like your collected photon by incident photon efficiency. Suppose if you incident a photon at particular wavelength, suppose if you're incident a photon at 780 nanometer of wavelength, how much photon the typical device is taking. You expect for an ideal device, you want to consume all the photons you get. Like photon is from the sun, right? So you want to get all the photons from your sun. But our device have some recombination, so it won't utilize all the photons to generate our charge carrier. So the number of charge carriers you are generating by the number of photons you incident, that is called as typical EQE of your instrument, EQE of your device. So to calculate that EQE, we need to have a chopper and we need to have a monochrometer. Sorry, I'm misspelling that, monochromometer or something. So that will incident your wavelength from 300 nanometer to 1100 nanometer wavelength. In that particular wavelength, you are gonna get your EQE percentage. So if you see in papers, like if you see in typical papers, you see the EQE graph starting from 300, going all the way to 800. That is
Yes,
for the
yes.
medium band gap solar cell. And for the low band gap solar cell, that wavelength will go up to 1100 nanometer. I hope it answered your question. Like if you have anything more, like.
Yeah, so here you don't show the EQV setup also, I think.
We will show you the EQE setup after we deposit the silver over there. We
Okay,
have that
okay.
one too.
Okay, thank you so
Because
much.
EQE setup is gonna take some time to set up. We will show you the setup today. If time permits, I will do some experiment on that one, or we'll continue tomorrow morning.
Okay, we have one more question from Muhammad Umar Rahman.
Okay, yeah, Mohammed.
He is asking, like, is direct reading of MPPT, maximum power point tracking, is possible?
Yeah, the maximum power point tracing is possible, but you need to change some of the settings here. So the maximum power point reading typically you will calculate for the solar cell with different illumination constants. So what you will do, you're gonna change your wattage here from 10 watts to 100 watts, and you will track the MPPT of that solar cell through whole device.
Okay. So basically we have to control the power of illumination, and by that we can control the MPPT.
Yeah, because typically you want to see your MPPT of the device with different illuminations, right? That's what we try to put in papers.
Okay, thank you, Raja.
Yeah. Any more questions here? Or if you want me to do one more device, we can just connect and do that one, or we can go for silver deposition.
Yeah, one more device you can do. Please proceed.
Yeah. Dr. Mukesh, if you want to add anything in between until I connect my device here.
We have two more questions, Raja.
Okay.
Ashok.
Yes, Nipun, you can unmute.
Yeah, so go ahead.
Ashok, I have unmuted you. You can ask your question.
Yeah, go ahead, Ashok.
Hello.
Yes, Ashok, we can hear you. Please ask your question.
So to measure the intensity of light, it is inbuilt power meter, or you have to measure any other external power meter with?
No, it's a inbuilt. Like we can measure the intensity of the light with this.
With
They have the standard
With-
solar cell basically.
with the standard the solar cell, right? So once you know like the current of the solar cell, so suppose the NREL already measured this one for me. So that is 1.64 milliamps. That's what we initially measured, right? The distance between the cell and the source. It optimizes our like Onsen illumination. When you have Onsen illumination, this typical device is gonna give you 1.64 milliamps of current.
okay. So
Yeah.
So you can vary that intensity using changing that distance between the source and that substrate, that device.
Yeah, you can typically change that one, but normally we do IV calibration with Onsen illumination.
Okay, so it is
And
you measure the
for
whole spectrum of that solar cell.
Uh, yeah, this will give you the whole spectrum because this is Onsen illumination, right? So it will give you from like UV to X-ray radiation, every radiation, like in the sun spectrum. So you are typically measuring in the mid afternoon, like when there is a mid afternoon and exactly you have AM 1.5 radiation, then that is called as Onsen illumination. The AM 1.5 radiation is called as Onsen illumination.
Okay, okay,
So the whole spectrum measurement is for EQV.
okay.
So any more question? Or?
Yes. One more question.
Yeah.
Mr. Said. Mr. Said, you can ask your question now.
Yes, my question is that when you have demonstrated that forward and reverse, it means you have varied your potential like from 0 to 1 and 1 to 0 like that?
Yeah.
Okay. Okay.
So it
Thank
is
you.
just like you're calculating from here to here and here to here.
Okay. Why this difference is there due to the material property of the cell like that or something else?
See, this history is different. Like when you apply a typical voltage, like when you get a typical voltage of 1 volt and 0 to 1 volt and 1 to 0 volt, the direction of your potential forwarding, like from forward to reverse and reverse to forward, is changing. So when there is a hysteresis difference, that means your material is not performing that well. You want very less hysteresis in the sample.
Okay. Thank you.
So we'll measure one more cell. Like these cells are with different conditions. So normally we dope some things and we do bilayer deposition, we dope something. So this is the dope device. In the earlier device we measured, this is the control device. Earlier device we measured is the dope device. So normally when we dope something into the device, we know the characteristics. Suppose we use a deoxidizing agent for not oxidizing SN2 plus to SN4 plus. As you know, the tin-based solar cells, they are prone to oxidation. So they will go from SN2 plus to SN4 plus, which will decrease their efficiency too soon. You're going to see that now. So that typical solar cell is with after 10 days of fabrication, it retained like from 6.2% efficiency to 5.9% efficiency. So it doesn't lose much efficiency after 10 days. This device having 6% efficiency earlier. Now we will see how much efficiency we are going to get. So I'm connecting to the same area over there. And the distance I kept the same. And you can show here like that's in the triangle or circle over there. See this one. This one is the current it's showing. And this one is the voltage. Okay. So this is 0.36 volts of VOC and the current is 24.96 milliamperes. See, for the previous device, when you saw that, the fill factor is 60%. And for this particular device, the fill factor decreased a lot, 47.6%. And the efficiency is only 4.38%. So for this device, efficiency decreased from 6% to 4.38%. That is like 1. What is that? 1.6% efficiency. And for the previous device, there is only 0.3% decrease in the efficiency for 10 days. I couldn't show you the 10 days before like experiment because that's not in this system. We just took it away. So that is decreased only by 0.3%, and this is decreased by 1.6%. So then, like now you know your doping is working properly. Then next step is to prove why your doping is working properly here. So for proving that one, we will do AFM, SCM, XRD, XPS. Like there are a lot of characterizations which will go on from here depending upon your doping. For me, I'm using sulfide segregation. So sulfide segregation is the thing you don't want to oxidize the material. You want to convert them to sulfur so that there won't be any p-type doping in the material. So for this one, there is a sulfur segregation. So the sulfur segregation we are gonna show that with FTIR and Raman. Okay, if that is little like it goes beyond the point of IV characterization, but I'm just saying we dope some materials, we passivate some materials, we try to reduce the potential difference in the grain boundaries. Like suppose there are grain boundaries and grains in the perovskite solar cell. So we want to passivate the grain boundaries so that there won't be any traps. You might observe when Dr. Chow told you, like you will see like when it is P-type material, you will see the positive peak, and when it is N-type, you see the negative peak in the grain boundaries. So that peaks, we want to reduce the peak difference so that there won't be any trap density. Like we want to reduce the trap in between the electrons. So in order to reduce the trap density and everything, we'll passivate the layers of perovskite. So this is a typical IV characterization. Any more questions before we go forward? Or if I'm going too fast, let me know. I can slow down.
No, that's fine. We have one question from Mr. Suraj. Suraj,
Okay.
let me read his question. How can we decide area of metal finger on solar cell?
That depends on your mask, like and how much area you're exposing to the sun. Suppose when I'm designing this particular mask, we already designed it in CAD with 0.04 centimeters per area. So before you design your solar cell, you'll know your area.
So Raja, his question is there. Are you using this one only exposed area or metal contact also you are this one considering?
It's only exposed area, Dr.
Yes.
It's not the metal contact area because you are not exposing that metal contact, so it's not generating any electrons or holes from there. It's not generating any charge carriers from that area.
Yeah, your light is not going through the metal because this one is metal, so reflected back. So only in between the fingers, we have to consider basically how much area is there.
Exactly. Sorry, I misunderstand the question, I guess.
Yes, yes.
So if you are clear with this IV, then we will go back to the system to deposit our silver.
Yes, any more questions
Yes.
from participants?
No.
Basically, this session is there. This one is for the interaction, this one. So wherever you have doubt, this one, you raise your hand, this one, we will unmute and you can ask this one. Yeah, Raja.
hello.
Yes.
Yeah, you don't need to wait till the end. You can just ask anytime, not a problem.
Raja,
Yeah,
I have one basic question. Actually, we are characterizing the cell here in normal conditions. So this natural light will affect the solar cell performance or not?
Yeah, for sure, it's gonna affect your solar cell performance because you don't know how much illumination you are getting. So in the morning, there is a different tilt angle. In the afternoon, there is a different tilt angle. In the evening, there is a different tilt angle. So if you see the solar farms or something, for adjusting their MPPT, they will adjust their solar cell direction also.
No, I want to ask that here you
Yeah,
are.
Amit, only demo purpose they are not switching off the light. Otherwise, during the measurement, they switch off light and then do this one characterizations.
Okay, sir.
Okay, otherwise definitely some small this one, because if direct light is falling, there will be a small change, not much this one, but when they are doing basically measurements, they switch off these lights.
One more thing, for doing this light, we don't get much sun here. It's snowing all the
Yes, yes. No, slight change is there because of, he is asking because of this one, your lights, this one, you are using the light sources.
Oh, this okay. Sorry, like I thought like something else, like total
No.
something. Okay.
So they switch off basically when they are doing the measurement.
Yeah, because when it won't affect much because we are giving the sun illumination over there, so it won't affect much.
Yeah, another thing is there because this solar cell is there. This one is the perpendicular and light is coming from the top. So is directly is not falling on the sample.
Yeah, when we measure the dark current, it will affect. Then we need to turn off the light.
Yes.
My question is regarding the area of the device.
Okay.
Because the contact, the pattern of the metal, it is back on the solar cell, right?
Yes.
So how we can consider the area of the device? Because on the front, on the all the area, the light is interacting with the material.
Okay, for this one, like to answer this, we need to consider the recombination also. So when there
And
is
I am
no
talking
metal
about the
contact,
area.
No,
yeah, that's
area,
what
for
like.
example, when they are exposing basically, because from the silver side, this light is not going. So only exposed area is there, that only they are considering.
No, so this is the front side. So from the front side, all the light is coming. Only from the back side, we are deciding the area of.
Mhm.
Only from the back side, the strip area basically is a solar cell area, right?
Yes. So from the back side, what you are doing, okay, in the front side, Raja, you are considering, because in that case, you have to consider the complete area.
No, Dr. Mukhi, because see, we have four fingers here,
Uh-huh.
and each four fingers are connected to something like some of these fingers, okay?
Okay.
Some of these fingers. So whatever the charge generating over that finger area, it's
Mhm.
going to the finger over there.
Okay.
So only will consider this area before the recombination. Otherwise, from other places, whatever it's coming, most of them will be recombining. So the cell area, what we consider is the typical area where we'll contact the solar cell.
So
So
basically,
we try.
you are taking only the silver area.
Yes.
Yes. Okay. So in between
Okay.
area, you are not considering.
No, we are not considering different area.
Okay.
We tried
So
etching out that area, but it won't show any difference.
yes. So basically, what we have to consider this one, because we are collecting charge only from the silver area. So we have to consider only in this case silver area, because light is
And
only charges are collected only in the silver area, not in between the area.
and one more thing, we can answer the question. Normally, typically when we are measuring, we will use this mask. So that complete cell is not illuminating. Only that particular area is illuminating.
Yes. Is it clear?
Yeah, yes, sir. Yes, sir. Now it's clear.
So what they are doing, because in between this one is light is crossing this one, because there is no electrode. So only silver area is there. That only they are considering when they are exposing from the back side, but they are making the both type of the sensor PIN and this one NIP. When from the front side, because there is no electrode this one.
So that
Yeah,
metal
this
area is decided by the metal patch, which is at the back of the cell, right?
Yes.
exactly.
Okay. Okay. Thank you.
Yes. Anything more?
Yes. Any other question?
Any other question? Okay. Yeah. If not, we will go to the silver deposition now. So as you can see here, this one went to 500 10 to the power of minus 6 millibar. This is good enough for my silver deposition. So now I'll select the process. This process 3 is for my BCP. Next menu, process, and I'll select process 1. Okay. Now this is process 1, layer 1.1. The charging is over, I guess. See? Okay. Okay. So I collected the process 1 area, and you can see the rate here. That is angstrom per second. In deviation, it's 100% because I selected the thin film area here. So if you show the process menu, edit, I calculated the final thickness as 1.000 kilo angstrom, which is 100 nanometer. So right now it is 0%. That's why it's showing 100% deviation from the area I made. And this is the thickness I'm depositing. So this sensor will show like how much thickness I'm going to deposit on this solar cell. And this will show the power. Normally, typically silver will start from 19% of the power for this deposition controller. It varies with your instrument. So in evaporator functions, we'll turn on the rotary holder. So when the rotary holder is turned on, it will help us to get the even thickness of the sample every area. Then we'll start the process and increase the power till 18. And we will wait for like 1 or 2 minutes to get the boat heated up. Like the one which we place the silver is called as boat. So until the boat heats up, we'll just wait for 2 minutes. Once the boat heated up, then we will open the shutter for silver deposition. So meanwhile, if you can see the layout here, the one over here, this pocket 2 is my silver pocket. So now, right now, I'm closing with the shutter. So once my power is reached, I'll open the shutter. So the silver starts deposition. So this CP1 is turbo pump. It raised to 100%. And this is vacuum pump 2, which is in the back of the machine. And this wall is used for refilling the evaporator. Like once we want to take out the samples, we will refill it. Okay. Now we waited enough time, so we go to the evaporator functions and we will open evaporator shutter 2. So once it's open, you can see the layout. This one moved to here, and my silver boat is exposed now. So now I'll increase the power by 1, and I'll see the sensor info. See the rate slowly started getting up from 0.00 to 0.01. So now I'm depositing at 0.01 angstrom. So what I typically want to do, like anybody is depositing, for first 20 to 15 to 20 nanometer, you want to deposit very slowly for even film. The next area is just the contact area so that you can deposit a little faster. So I will deposit at 0.2 angstrom per second initially, then I'll go to 0.3, 0.5, then finally I'll go to 1 angstrom. So you increase it, wait for some time until the board heats up. So go to the sensor info, now the rate is changing, it's 0.02 now. 0.03. When your sensor's life goes bad, it's gonna fluctuate a lot. We can do this one in auto mode too, but I get accustomed to manual mode. We can try auto mode when we get time. And you can see here the chiller is reached to 13 degrees centigrade. This is flowing water to my vacuum pump from these pipes. So the more mean free path you create for the electrons, like the more you have less pressure you have, more time it will take to deposit the silver on top of your cell. But lesser mean free path is bad because it will create more contamination in your cell. So now it went to 0.1 angstrom. Okay, 21. Yeah. We can't show you what's happening inside the evaporator because it's completely enclosed. We just need to see like this evaporation and all these things. So initially it was at 5 to 10 to the power of minus 6 millibar, but now it jumped to 8 to 10 to the power of minus 6 millibar because of silver evaporation. So before depositing any material, you need a couple of trials. You need to see how much power it's gonna deposit. If anybody is trying to deposit C60, I'll tell you it's much harder than silver because the boiling point and melting point are very nearby. So if you just increase the power by 0.2 or 0.3, it's gonna evaporate all at once and you can't control the deposition rate for C60. So C60 need to be much higher. You want to deposit at 0.05 angstrom, not more than that. So for first 2 nanometer, I deposited at very low rate. Now I'm gonna increase the rate a little bit. Because after first 10 nanometer, all you're gonna deposit is for the contact area. And when you are depositing initially, if you put the higher rate, there is a chance of diffusion of silver to your perovskite layer. Then diffusion of your metal contact is bad. It will create your more shunt path to the perovskite and your VOC will be very low. You want to add anything, Kishan? You want to add anything? You want to explain anything in the middle? Good? Okay. Okay, perfect. So now I'll go to 0.5 angstrom per second and I'll deposit till 150, 15 nanometer. Then I'll increase it to 1 angstrom. So it's 0.49 angstrom per second now. Here. And the thickness deposit is 7 nanometer till. So probably this process will take like 30 minutes. And in 30 minutes, we are going to deposit like 80 nanometer of silver, 80 to 85 nanometer of silver, which is good enough for our electrodes. The one thing you don't want to do with this one is diffusing your silver electrolyte, like silver electrode to the perovskite. You don't want to diffuse that. Right now, it's 10 nanometer deposited on top of like the 0.111 angstrom is at 11 nanometer. Now, each 0.1 power you increase, it's gonna increase rate by a lot because the boat is heated up and it's the silver melting point here. I increased just by 0.1 from 22.9 to 23, and it's already went up to 0.8. So now I'll go to 1.2 angstrom and deposit a little faster. So if it's kind of boring, if you have any questions, you can ask us.
Yeah, participants, if you have any question, you can ask. Have few
From
minutes.
IV or this one, and after this, like we may disconnect. Like after this deposition, we may disconnect for 2 minutes or 2-3 minutes to go to the other lab to show you guys the ETV instrument.
Okay.
So once we deposit this 800 nanometer, we will stop this one. We will let it. We will let the vacuum pump to stop, which may take 20 minutes. Then we will refill it and show you the devices after fabrication. So this is our pressure trends from last 24 hours. The bottom green line, a small green line you are seeing is the oxygen level. When your glove box is in good condition, normally it's at 0.1, but it's up to us how we maintain it 0.1. So frequently you need to change your carbon filters, like HEPA filters, and for every 3 years you need to change your metal pellets. Uh, that one is this is the copper catalyst we changed, and this one is the molecular sieve for absorbing the moisture and oxygen. Enough charging? Is there enough charging in the model? No. Is there enough charging in the model? Yes. So right now it's 53 nanometer deposit. We just need to deposit more 30 nanometer. Initially, when we started, the life of the sensor was 98%, and this decreased to 97.59% because of depositions. Like 3 depositions are there. One is C60 and BCP. After that, I deposited silver now. So this life is decreasing. So after some, like after maybe 5-6 fabrications, that will go below 90%. Doesn't mean your sensor is bad at 89%, but just be like we'll be more careful, like because the sensor cost is much lesser than your fabrication cost for each fabrication. Three minutes, no? 3-4 minutes. rates, decreasing the rates. Oh, that one is due to the silver, like the silver. There is less silver on top of the board now because the silver is evaporated. Each pellet can deposit like 1 nanometer, right? So there is very less silver left. That's why the deposition rate is getting lower. So we have 80 nanometer thickness of film now, and we deposited in 21 minutes, 21.19 minutes. We are good enough for our silver deposition. So we'll just stop the deposition, stop the layer, and abort. Now you can see the rate is decreasing, and we'll close the shutter here. So we'll go to the evaporator functions, close the shutter too. Once the rate reaches to 0, then stop the rotary holder. Then we will de-evacuate the system. So we'll start the turbo pump 1. So this turbo pump 1 don't stop immediately. It takes some time to stop. So right now it's at 99%. It needs to come to 0% in order to refill our evaporator. So this pressure will come to 10 to the power of -3 millibar. Then we'll come back and start the refilling and show you the samples. So meanwhile, if you guys don't have any questions, we will disconnect for 6 or 7 minutes to go to the other lab and introduce the EQV instrument to you people. Is it okay with you, Dr. Mukesh? We may disconnect for.
Yes, yeah, no problem. This one.
Yeah,
we can take
perfect.
like a 5-minute break and then again.
Yeah,
can...
just take 5-minute break and I'll introduce to the EQV system. And we'll come back and see like how the silver is deposited on top of the samples.
Yes.
Okay. Thank you.
Thank you. So yeah, participants, if they have any doubt, they can ask. Otherwise, we can take 5-minute break.
Yes, we are back in the lab. Like, I don't know if everybody is back or if you need more time.
Yes, yes. Yeah, you can continue, Raja.
Yeah, thank you, Dr. Mukesh. So I just want to introduce to this lab. This is the pouch cell fabrication lab. So we do synthesis of the material and pouch cell fabrication in this lab. This is one more glove box we have, but this won't have any evaporator. This whole glove box is dedicated to battery fabrication. And if you can follow me, so this is our optical table, and this whole instrument is EQE. So this is the external quantum efficiency instrument. This one is called as monochromator, and the one here, the black one you are seeing, is called as chopper. And this one you'll know, like xenon arc lamp housing. And you'll follow all this manual. Like once you start working on this, we need to follow all this manual to set up the instrument. So you'll see each and every instrument in the manual over here. So we'll quickly introduce to each and every instrument here. So this is the optical chopper. This one is called as optical chopper. Optical chopper will chop your light. Like it will create a thin slice of light to go through the chopper to shine on your solar cell. So it won't somebody asked me, how you consider your area of your solar cell. So when you measure the current in that current in the IV system, suppose you will get 20 milliamperes per centimeter square. This optical chopper won't depend on any area. It will create a small amount of light which can create particular charge carriers from EQE. Like EQE to JSC, there is a calculation, or in online portal also you can find how to convert from EQE to JSC. So if both of them are matching, then your area is proper. The calculated area is proper for your instrument. And this is SRS 810. So this one is called SRS 810. And this one is the power supply for my xenon arc lamp. So if you turn it on, and this is the lamp. So right now its lamp power is 0 watts. When you turn it on, 300 watts lamp power. And this is for adjusting the chopper. So for chopper adjustment, you're gonna connect this one. See here, this cable will communicate this one to the chopper. And this instrument will control how much voltage you are applying to the measuring instrument. So these are two of my measuring instruments. This is called as detector, DETL-SIUV. So this is my detector, and this is my solar cell for the measurement support, like supplied by the Newport. So if you can see here, this one is calibrated and supplied by Newport for the QE solar cell. QE is quantum efficiency. So there are two types of quantum efficiencies. One is internal quantum efficiency, and other one is external quantum efficiency. Like we can't show all the measurement process today, but for sure we will show you tomorrow, because it takes like 1.5 hours to introduce all the system to you people. So we'll introduce the components today. Tomorrow we are gonna do like how we measure EQA for a typical solar cell. So we'll turn on this one from the back. And we'll turn on the chopper here. This is the monochromator. So I turn on the monochromator. That sound you're hearing, that is adjusting the position of your monochromator, like for the particular wavelength. So TrackQ Basic, this is the software we use to measure our EQE. So this is the monochromator detection instrument. If they are connected, it will show in the green color. If they are not connected, it will convert to the red. And suppose if we go to the wavelength, 555 nanometer, can anybody tell me what's the color at 555 nanometer wavelength from the audience? What's the color you expect from 555 nanometer in WebGL? Okay. So
Yeah, actually, yeah, we have to unmute them. They are muted.
okay, not a problem. So
Somebody has replied green.
yep. So you can see here, like after the
Yeah,
chopper,
green.
when you put 555 nanometer, come here. So that will be the green color. We can adjust the wavelength from this monochromator. So if we typically put like, let's say go to the wavelength 770. I couldn't see anything because that is in the UVIR region. So maybe I'll go to 440. Let's see if it gives something. I'll go to 440. It's okay. See the color here. So each wavelength, so this typical instrument can scan from 300 to 1100 nanometer wavelength. So it will show you how your device is performing at each wavelength. So suppose at 400 nanometer, how many photons you are absorbing. For 500 nanometer, how many photons you are absorbing. So if you take a device with 1.51 electron volts, you typically assume it will absorb all the photons until 770 or 780 nanometer. So you'll know like if it is 1.51 band gap, that is 1240 by 1.51, that will give you your wavelength of absorption. So you typically assume like it will absorb all up to 770. But when you see the EQE of the instrument, so I'll load one data. Let's see if I have anything. Yeah, if you can see here, like this is the EQE measured earlier. The QE percentage, that is the number of electrons generated by the number of photons absorbed, that is only 60% at 300 nanometer area. The region over here will show you the back contact, means that's the first layer recombination. And the region over here, like the right side, will give you the last layer recombination. So if there is a band mismatch or band alignment mismatch, then you will see this area is decreased. So my bottom area, I need to optimize the bottom area. That is, if this is a PAN structure, then I need to optimize the whole transport layer. If I get lesser EQ here, then I need to optimize the electron transport layer. That's the back layer. And the one you are seeing, the dip you are seeing, that is because of the reflection of the solar cell. So for typical silicon solar cell, in order to avoid the reflection, we will do patterns. So the patterning of the solar cell will be done to improve the efficiency in this mid region. So this particular EQ is for my MAPBI3 solar cell, which is having 1.51 electron band gap. That's why it is absorbing all the photons till, like if you can draw a perpendicular line from here, it will be up to 790. And after that, it won't absorb anything because it's beyond the band gap of that solar cell. So this is our typical EQE instrument. And for measuring that, first we will measure the detection instrument. And after that, we will measure the solar cell given by the new port to adjust everything. So once everything is adjusted, you are typically gonna see a spectrum like this. So this is the solar spectrum for all the wavelengths. So once you do the detection instrument with proper calibration and everything, you're gonna see this type of graph in your Trackio software. So once you see this, you're gonna do your device also, and those two should be perfectly aligned but not matching. So this bottom line you are seeing, this one is from the detection instrument, and the top line you are seeing, that one is from the solar cell supplied by the new port. So after those, then we will calculate QV for the instrument. This is for the typical solar cell supplied by the new port. It's almost nearby 100% for this region, for the top region. That means the reflection loss is very less, but there is back contact and front contact losses for this device. So this device band gap is typically 1.12. That's why it's absorbing till 1100. So that's about EQE. Yeah, since if you have one more hour time, I can show you this instrument right now. But since we need to show you the refilling over there and the instrument also, so we are gonna stop EQE till here, this till the introduction. Then I'll show you like how to operate this instrument tomorrow in the morning session. Any more questions for EQE before we go back to the instrument like our evaporator? Or any more suggestions for me? You're welcome.
I guess we don't have any questions, Raja, but you are explaining so perfectly. No more
Thank you.
suggestions for you. Yes, yes.
Thank you very much. So yeah, Dr. Mukesh knows about this instrument. It takes some time to operate. That's why I couldn't show you today, but I'll for sure will show you tomorrow. Yep. Again, we need to go back to our lab, which is in the other place. So we'll go back there and contact you back like in 5 minutes. We are sorry for this delay because these two labs are in separate buildings.
Okay, okay, no problem. That's okay.
Yeah, no problem.
Thank you. Home needs to be 2% more, like that 2% needs to be 0. And our pressure is already decreasing, like it's stated of -6 earlier. Now it's stated of -3. So we wait for 1 more minute, like it is go to 0%. Start repeating this.
Raja, sorry to interrupt you, but your video is quite blurred and your voice is also breaking.
Can you turn on the Wi-Fi? Sorry. Ask if it's good. Let's see the Oh, hang on. Wait a second. That's my mute. No, it's on screen here. Okay. Give it to me. Sorry. Can you hear me now? Okay. Yeah. Can you hear Dr. Mahesh? Can you hear me?
Yes,
Yes.
Yeah.
Now
Wow.
yeah.
Okay. So this TP1 is 0% right now, and my pressure is 310 from -6. So I'll turn off my vacuum pump, and I'll turn off the chiller. Now it's peaceful. So we'll refill the evaporator. Like we'll refill it. It may take like a couple of minutes to refill. So now it's already 6 millibar. So when it goes to the atmosphere, like it will show atmosphere, like atmospheric pressure, then we can open the inner door of the glow box. So meanwhile, I'll just go in. I'll get ready to take out the samples. So once this is atmosphere, go to the evaporator functions. And this evaporator inner door, the white one you are seeing here, that will be highlighted. And you just need to press on the inner door, okay? Now it's 180. 190, 200. It will take like 2-3 minutes to come back to atmosphere. Then we will show you the solar cells deposited. I think we should be good with that. So you can see this wall, like this box wall, is purging the air in. Not air, it's nitrogen. Nitrogen. It's okay. That's the machine sound. More 600 millibar, then we'll be at atmosphere. 1020, right? Atmosphere, yeah, more than 1000. So So somebody asked a question before, like when we know we need to change the sensor, right? So you can see the difference between the sensors, the deposited one. There is a lot of silver deposited on this sensor, whereas on this sensor, there is not much deposited. So we change this sensor, this health is low, like the life of this sensor is low because a lot of deposition went on top of this. This one is okay. You can see some silver is deposited on top of this one too. So what's the level of pressure? 660, 670, 680, 690, 700, more 300. Oh yeah. This is the mask we use to deposit C60 and BCP. So this mask don't have any fingers, so I can deposit all the C60 and BCP here. And this is for my AG finger. This is in-house design. That's why it looks a little messy. It's not from the manufacturer. Yeah, 40, how much? 850. A little more. 860. Yeah, it's gonna slow down for one, like in 1 minute, it's gonna be done. $890, 900. $920. The sound you're hearing, that is called refilling. So once all the nitrogen went out because of evacuation, now we are purging nitrogen inside. $960. More 30. $20. Listen, any more questions in the chat box? No? Okay. Good. Okay. Now it's at atmosphere. Now it is showing at atmosphere. So go to the evaporator functions. Why it's not it? Right. Go back. Need to wait for one more refill again. So turn off the refill. Turn on. Press on that. Yep. Then go to the evaporator functions now. Evaporator functions. Yep. Evaporator inner door. You can show here. So you open the inner door. Now press on rotary holder. Stop it. Now you need to stop it exactly at place. Okay, turn it on. Turn it off. Yep, we're good. So you can see there is no silver on top of it now. Like the silver is all gone over here. Taking this now. This is the solar cells and silver is on the bottom. So these are the silver electrodes. Other side. Okay. These are the silver electrodes after our evaporation. So the right one you are seeing here are the bottom electrodes and the left ones are top electrodes. So now after this, we are going to measure IV and EQ for these things. So for in this fabrication, we have like 6 conditions. Like for 12 samples, we have 6 conditions. So for all 6 conditions, we are going to measure IV and EQ. So that's how we're going to deposit silver and all the things. Any questions for this? Can't hear anyone. Can you hear me? Oh, Vichani, can you hear me? Okay. Any more questions from the other side? Oh, I guess I'll sleep now. Hmm? Very nice. Mr. Amit, Dr. Mahesh, like any more questions, Dr. Mahesh?
Yes,
from the-
Raja. We have one question. Just now
Okay.
he has raised his hand. Mr. Said,
Okay.
you can ask.
Yes, yes. Yeah, after the
Yes.
evaporation, did you measure the sheet resistance of this deposited silver thin film? What is the value?
That's a good question, but we never measure sheet resistance of the silver deposited because we believe that's for the contact, and yeah, that's a good thing to do. I'll measure and let you know.
Is there the sheet resistance will impact the device performance?
I know the bottom sheet resistance, the ITO sheet resistance will impact the device performance. But the top resistance, since this is the silver, I don't think, because it's highly conductive. So I don't think it will impact the efficiency much. But
Because
for the bottom
sometimes
resistance, for sure, ITO.
sometimes due to the very less thickness of the material, its resistivity sometimes get increases other than the bulk material like that.
Yeah, true. But 80 nanometer when compared to your 300 nanometer thickness is good enough.
Yeah.
I know, like for heterojunction, heterobulk junctions, I know, like for the lower area, it will impact the roughness. When you go to the ITO, it is only 40 nanometer thickness. That's why we care more about sheet resistance. But silver, it is 80 nanometer. So that's why we didn't care much about it. But yeah, that's a good thing to do. I'll measure and I'll let you know.
Also, one thing that when the thin film of the absorber layer material has been developed, so is there any chance of pinholes availability on the thin film like that?
Oh, there is a high chance. There is a high chance of pinholes. That's why we need, before finishing our instrument, we need to make sure that our deposition conditions are correct. Like in lab to lab, the deposition conditions vary. So suppose your dripping matters, your perovskite solution thickness matters, your filtering matters. So when your filtering is not good, when there is a contamination in the nitrogen glove box, or when the deposition, like when you drip the anti-solvent in the wrong time, then also you're going to form many pinholes in the perovskite. So that's why we do SCM. beforehand to make sure our deposition conditions are right.
Mhm. So the spin holes after deposition of silver may creates the uh, shunt resistance
Yeah,
low like that.
exactly. That can create shunts. Like that's why before you finally fabricate the cell, when you are developing your materials, like suppose I am developing a MAPBI3 solar cell, then in first few fabrications, I make sure my conditions are all right. The spinning speed and the deposition rate, in the thickness of the film I'm using. So I make sure everything is right without pinholes until I don't make final device and see like, okay, I have pinholes and I got the resistance. So first we will optimize the film, then only we'll deposit silver.
How to
Yeah,
analyze the pinholes by the same imaging like that? Because this gives a very small area, and if within a 1 centimeter square, 1 to pinholes is like very few holes, pinholes is sufficient to making the shunting like that.
yeah, very few pinholes are enough to make the shunting of that one. But when you know, like in SEM, you don't measure only one area. You will go to different areas and measure that one, right? Like it's not only one area you're doing.
Oh, okay.
Yeah, so you'll measure different areas and see like which area you're forming pinholes. Maybe suppose in dripping also, there are two types of dripping you can follow. The one is line dripping. One is the center form dripping. So center form is dripping is you'll just dripping the center. Line dripping is you will start from the top and go till the bottom to drip your anti-solvent. So the dripping conditions, the spinning conditions, the temperature you are using to handle the film, there are n number of things which can impact your film quality. So we need to optimize everything before we go to the silver.
Okay, thank you.
Yeah, that's a great question. Thank you, because I got the same question when I joined. So any more questions or something? Any other comments? For evaporation, for IV, for EQ, yeah, we're gonna do tomorrow. But for remaining things, if you have any questions. Okay, if not, let's wrap it up for today and let's meet tomorrow morning again.
Yeah, one more question regarding the thing
Yeah.
that the metal deposition.
Okay.
Sometimes when we are depositing the metal, the
Okay.
nature of the metal is not much sticky. Some amorphous nature is there. So, is there any possibility due to the very high deposition rate or some other things? Like here, we are seeing the very shiny, good film.
Yeah,
So
that's due to deposition rate. We see a lot of amorphousness of the films here. The higher deposition rate in the starting itself can cause the amorphousness, or the oxidization of your silver pellets can do that one.
It also depends upon
So,
the what material we have used.
yep.
yes,
It depends on the material too.
yeah, sometime we have to deposit some adhesion layer. For example, if you are depositing on silicon, before gold, we have to deposit titanium or some nickel or chrome.
Yeah.
So
And
similarly,
even
depending on which material you are depositing, because here silver adhesion is good, that's why they are using the silver.
Okay, thank you, sir.
actually, frankly speaking, aluminum is more better, but we can't deposit aluminum in a particular thickness. Like we can't control the aluminum thickness properly in our evaporator. That's why we go for silver here.
Generally, we are
Yeah.
facing this problem with aluminum when we are
Yeah.
using aluminum as a contact. So the nature is not much shiny and not much sticky. Some amorphous nature on the top we are facing like
Yeah,
that.
we face the same issue with aluminum too. That's why we are going for silver nowadays.
Mhm.
So that aluminium, like as I told you, it depends from material to material. Like you need to optimize a lot of things before you get a significant.
Okay.
Yeah. So, for rotating camera. Okay, anything else that you need to discuss?
Yeah, I think we can continue tomorrow this one. Already you have showed this one devices, how to characterize this one. Yes.
Yeah. Yeah, we can characterize this one tomorrow morning. Like I'll do IV today for this instrument for this sample, and we'll do like I'll be ready with EQV tomorrow morning when we start the work.
Yes.
Yes. Thank you very much.
Yeah,
you, sir.
thank you, Reza, for showing this one, this complete testing, how to characterize basically solar cells. So if participants, if they have any question, this one, tomorrow we can continue this one. So yeah, thank you very much for joining this one, this tutorial. So yeah,
Thank you, everyone.
yeah, Amit and Nipun. Now I
Thank you,
think we
sir.
can close the session.
Yes, sir. Yes, sir. Yes, sir. Sure. Thank you, Raja. Thank you, Poojan and Yushin.
Yes.